In this video, I'm going to talk about the second derivative test. The second derivative test tells whether a critical point is a local maximum or a local minimum. If you have a function y equal to f of x, to find the critical values, you have to find f prime of x, set it equal to 0, and solve it for x. If you find, for example, x equal to a as a critical value, then to find the critical point, you have to substitute x equal to a into the equation of the function and find the y value. So then you can say the point a f of a is a critical point. This critical point can be a local maximum, a local minimum, or neither. To check the type of this critical point, we can apply the second derivative test. Here's the test. If you evaluate f prime of x at x equal to a, and if the answer is positive, then you say a f of a is a local minimum. And if f prime at x equal to a is negative, then a f of a is a local maximum. And if f double prime at x equal to a is 0, that the test is inconclusive. So we can't make any conclusions about x equal to a. One easy way to remember this test is to think of this diagram. For example, for f double prime at x equal to a greater than 0, we said we have a local minimum. If to find f double prime, you're differentiating f twice, and the result at x equal to a is a positive number. So I'm just going to put two plus signs here to show that we are differentiating twice, and the derivative is positive. So then we say in this case, a f of a is a local minimum. So then the shape of the graph is something like that. So you see we have a smiley face. So if you are a positive person, you will be happy, you will be smiling. And therefore, we have a local minimum down here. For the other case, we said if f double prime at x equal to a is negative, then a f of a is a local maximum. So again, you're differentiating twice, and the result here at x equal to a is negative. So I'm just going to put two negative signs. And here, since we had a local maximum, the shape of the graph is like that. So it's like a sad face. If you are a negative person, you look unhappy, you look sad. So these two diagrams would help you to remember the second derivative test. Now, as an example, let's look at a function y equal to x to the power of 4 minus 4x to the power of 2 plus 2. I'm going to start with finding y prime. So by differentiating this equation here, it's going to be 4x to the power of 3 minus 8x. Now we set this equal to 0 to find the critical values. If you notice, both 4x cubed and 8x have 4x in common. So I'm going to remove 4x. So then I'm going to be left with x squared minus 2 equal to 0. So if this expression here is equal to 0, we have two options. Either 4x is 0 or x squared minus 2 is 0. If 4x is 0, then x is 0. And if x squared minus 2 is 0, then x squared is equal to 2. Therefore, x is equal to plus minus root 2. So 0 plus minus root 2 are our critical values. To check the type of these critical values, I'm going to apply the second derivative test. So first, I need to find y double prime by differentiating this y prime. So y double prime is 12x squared minus 8. Next is to evaluate this y double prime at x equal to 0, at x equal to root 2, and at x equal to negative root 2. So y double prime at x equal to 0 is 12 times 0 to the power of 2 minus 8, which is minus 8. And this is a negative number. Based on the second derivative test, if f double prime at x equal to a is negative, we have a local maximum. So then you can say at x equal to 0, we have a local max. Next thing is to evaluate y double prime at x equal to root 2. So that's going to be equal to 12 times root 2 to the power of 2 minus 8. And that would be 24 minus 8, which is 16, and that is positive. So then you can say at x equal to square root of 2, we have a local minimum. And then finally, at x equal to negative root 2, we get 12 times negative root 2 to the power of 2 minus 8, which is going to be again 24 minus 8, and that's 16, and that's greater than 0. So then you say at x equal to minus root 2, we have a local minimum.